Okay, okay, let's go ahead and start the class. I've written some equation on the board over there. Online students don't see that board, but you should have the equations in the book or in your notes. Basically, they're there because you want to go back to them at the end of the class and solve an example using these equations. So I don't want you to go back to your notes and find it. You can have them readily available to you on the board. Okay. Is there any questions before we start the lecture about the material from last week? Okay. Let's go on. So we are gonna, as I said, we're gonna come back to these. We're gonna solve a couple of example problems based on the things we discussed in the previous lecture. But today we are going to start with some new concept. The first one being the center of pressure. Okay, center of pressure. So far we have seen that the effects of flow moving over an object is felt by the object through the normal pressure and the shear stress. This is something that we have talked about. This is how flows communicate force or communicate with objects in general, right? Exert force on objects. Yeah, this is what we have seen. The result of this is going to be a resultant force. Let's call it the resultant force R. And depending on where you put the R, which point of your object, you are going to get a net moment as well, right? So this resultant force and moment are the result of integrating the normal pressure and the shear stress over the whole surface, the lower and the upper surface of your object, right? And we have seen all of the ways to calculate those integrals, essentially, to calculate the final forces and the force coefficients in the previous lecture. But today, we are going to see whether it's possible to find a location on this object that let us have only one resultant force. So no moment. Let us represent the effects of this pressure, normal pressure that is present everywhere on this object, and the shear. You get the idea, right? Let us represent all of this with only one force. We want to investigate whether it happens or not. Okay. You have already seen if you want to find the resultant force on the leading edge, we will definitely or most probably have a moment at the leading edge as well, right? And we already have the equations to calculate this moment and this resultant force, the components of it, actual force and the normal force, right? Or the lift and drag based on your directions of the coordinate axis. Okay. Let's call this R. Let's call this F and the other one R. Okay. So essentially what that means, if this is a combination, if this whatever we have at the leading edge is the combination of all the pressures and the shear stress that you're going to feel on this leading edge, what we're going to have here, the force we're going to have here, has to exert the same moment as all of the pressures and the shears on the leading edge, only in the other direction, to cancel out that moment. Does that make sense? So let's go again. Let's actually see. All of these forces, the pressure and the shear forces, exert the moment at the leading edge, right? And we can represent the combination of all of them with the resultant force, right? We are looking for a point inside this body or outside of it, right? At which we can represent this resultant force and moment with only one force. What does it mean? It means that whatever moment the forces on this point applied to the leading edge must cancel the total moment that is being applied by all of these forces at any point, essentially. Okay? That's the idea. We are looking at that. We want to find that point, right? That can exert the same amount of point. That's the goal, right? We want to find that point. Is this clear? Okay. So based on this, the moment at the leading edge, and we are looking at two-dimensional body. So this is M prime, has to be equal to the negative moment that is being applied by the force at this point. Okay? How can we calculate the moment that is being applied to the leading edge by this force? It's the force multiplied by the distance, right? Let's call that distance x. So, and let's assume that the leading edge is at the same actual direction as the point we are looking at. Right? So that's the only assumption we are making. So the only force that is going to exert some sort of a moment on the leading edge at this specific point is called the n prime. The moment that is being applied is going to be n prime multiplied by x. So again, we are looking for an arbitrary point which can represent all of the forces and moments. Which can replace all of the pressures and the shears we have on the surface by only one force, not a force and a moment, only the force. Right? Yes. This is F, okay, and this is R, which has two components, N and A, right? But both of them can be R, right? The reason I used different names for them was to avoid confusion, I guess. So, as long as we can calculate the moment on the leading edge, we should be able to find a point inside or outside of this object that exerts the same moment on the leading edge as the pressures and the shears on the object, right? And that distance is going to be called the center of pressure. So this was the mathematical definition, which can get a little confused. But let's see if we can have any physical interpretation of this. Essentially, what we mean by center of center of pressure, what we are looking at is a point at which, again, I'm just reiterating what I just said. earlier, maybe in a little different language. Let me just clean the board. Okay, we have pressures and shears, right? These pressures and shears, let's look at this point, will exert some moment at this specific point, right? All of them, each one of these pressures and shears. Does that make sense? And let's look at the pressure. Let's look at actually this pressure. Let's look at the pressure that is being exerted on this point, or let's look at this pressure and compare it to this one. Let's say they have the same. We have the same pressures at these two arbitrary points, 1 and 2. Okay. Obviously, they have an arm when it comes to this point, so they are exerting a moment on this specific point, right? If this distance, of course, is the same, what will be the resultant moment? Let's say we only have these two pressures. Actually, I have to move this here. Let's say we have a pressure here, this arm is exactly the same. The only difference is going to be the direction of pressure. They are going to be applying two moments at this point, two exact same moments at different directions, right? Which means that you're going to get 0 moments here. That's the idea of center of pressure. So all of these pressures and shears apply a moment on each location of the body. We are looking at the point at which all of the moments will cancel each other out. Okay? So since we already can calculate the moment at the leading edge based on the equations we have, and we usually the center of coordinate system at the leading edge. So that distance, the distances are usually calculated from the leading edge of an airfoil. Use that mathematical definition, the distance from the leading edge. And it is called x of CP. Is this clear? Yes. Pardon me? We are not really concerned with the center of mass here, mainly because, okay, let me ask you this. What is the definition of center of mass? I think we got disconnected here. What is the definition of center of mass? Okay, center of the object, right? So, is the center of mass, we lost the video feed here, so I have to fix this, sorry. Give me 1 second. Okay, does that definition has anything to do with the forces that are being applied on the object? Okay. Does the definition of center of pressure has anything to do with the distribution of mass in the object? Not necessarily, It does have everything to do with the flow that is going across the object and also the geometry of the object. So the two may be on top of each other, right? But the definitions and the applications of the two definitions are going to be different for us. And in this course, we are mostly concerned with the flow over the object, so we don't really care about the center of mass or center of gravity for that matter. If you are interested to do some center of gravity and mass analysis, you should, in aerospace industry, you should take the flight mechanics course. Just, that's it. I guess extra information. Okay, any other questions? So hopefully we understand what the center of pressure is. What is the base point for its measurement? So we have the leading edge. This is going to be the center of your coordinate system, x and y, and the distance from this leading edge at which the moments cancel each other out is called the center of pressure. Why is this an important concept? Essentially, it's going to reduce some variation and some complexity from our system. If we use the center of pressure as the point we are going to put the forces on and do the analysis on, we are essentially removing the need for calculating the moment. Does that make sense? Okay. But as you are going to see later on, center of pressure is not used that often in aerodynamics. Why is that the case? Let's take a look at the equation again. So we said x of Cp is equals to n prime over, m dot prime over n prime, right? M dot prime Le over n prime. It is very important to do the moment at the leading edge because we are defining this distance as the distance from the leading edge, right? If it was defined as this distance from the trailing edge, we should have used the moment at the trailing edge. Does this make sense? Okay. So why is the center of pressure not a very useful concept when it comes to general aerodynamic analysis? It's because of the fact that if you decrease this force, what is going to happen to your center of pressure? It is going to change. It is going to go further and further away from your leading edge. And at some point, it will go to infinity at the limits, right? So the fact that it can change with the angle, changing the angle of attack, and changing the velocity and all of those things, essentially changing the forces that are being applied on your object, make it a little bit useless in our analysis because we are going to lose the consistency we need, right? Later on, we're going to see that we are going to use, especially in lower speed flights or in lower speed aerodynamics, we are going to use the quarter chord as the reference point. The quarter chord is defined as a point that is just 25% of the chord length away from the leading edge. Why do we do that? We're going to discuss that later on. What you're going to see is the quarter chord point is used more often as the center location, as the reference point in aerodynamic analysis. Any questions so far? Good. Let me ask you this. Can we find a relationship between the center of pressure, the quarter chord, and the moments at the quarter chord and the leading edge? Think about it. So let's say this is your quarter chord. The only force that is going to generate any moment on the leading edge is going to be n prime, right? Based on definition, let's call this n prime of quarter chord, C over 4. And let's call the moment that generates n prime of C over 4. We have n prime of the leading edge, we have the N prime at the center of pressure. And we also have this distance, x of Cp. We want to find the relationship between the moment at the coronal core, this distance, center of pressure, and the moment at the leading edge. The first question you need to answer is whether we have the distance from the leading edge to the coronal core. That's it. That comes from the definition, right? You don't need to do any measurement or calculation, right? Okay. Any ideas? Think about it.
Could you restate the question? Sorry.
Okay, I want you to give me a relationship between the moment at the leading edge, the coronal core, and the forces at the coronal core, and the center of pressure. We already know this relationship exists, right? M prime LE is equals to negative x of Cp N prime. For a case with zero angle of attack, this N prime is going to be L prime, but we'll get there later. How can we relate the moment at the coronal core? How can we calculate the moment at the coronal core? The moment that is being exerted at the coronal core by this N prime at the center of pressure. No. Just a simple equation like this. You don't need to take any negatives. Okay, let's do this. So what is this distance here? This distance is x of Cp minus C over 4, right? Okay. So the moment at the coronal core, the moment that is being exerted on the coronal core by this orange N prime at the center of pressure is going to be negative x of Cp, the distance between the two, minus C over 4 multiplied by N prime. Right? Is this clear? Which color is better for you? This one? Orange? Yellow, orange, whatever it is. Let me write this again. So moment at the coronal core. Moment that is being exerted at the coronal core, by whatever, is going to be negative the distance between the coronal core and the center of pressure, which is x of Cp minus the coronal core multiplied by the force at the center of pressure, N prime. So let's multiply this here, x of Cp multiplied by N prime minus or plus C over 4 multiplied by N prime. This itself is the moment at the leading edge. So the moment at the coronal core is going to be negative moment at the leading edge plus C over 4 multiplied by your force, N prime, normal force. You're going to see later on that this cordial cord is important. We're going to go over this later in chapter 2 or 3, I think. But the cordial cord is important because the moment is not zero there, but doesn't change with angle of attack. The moment remains roughly constant. So as long as you have moment at one angle of attack at one condition, you essentially have the moment at the rest of angle of attacks, right? That is going to help you a lot. Essentially, if this moment remains constant, you already have C of 4, that's by definition. If you have L prime for some condition, you should be able to calculate the moment at the leading edge for that specific condition, or the center of pressure for that specific condition. Does that make sense? Okay. So let's move on from this. This is something we should have covered in the previous lecture. It's related to the topics of the previous lecture. We're going to talk about the flow similarity. Flow similarities now, or dimensional analysis. Dimensional analysis. Before jumping into this discussion, we need to be able to answer this question. What are the physical properties or physical quantities that can determine the variation of the aerodynamic forces? The resultant aerodynamic force, we usually call that R. So what are the physical quantities or properties that can determine the variations of that R? Or, to put it in layman's terminology, whatever you call it, what does R depend on? R is a function of what? It's not layman's term. Pardon me? The angle of attack, alpha, that's correct. What else? Chord length, that's correct. Or to make it a little more general, the geometry. But since we usually characterize the geometry with chord length, we have the old tables, we are going to only use the chord length, right? What else? Normal force is a component of the resultant force, right? So you can actually write this function as two functions, n as function of whatever, a as function of whatever. Span area, we are talking about the two-dimensional case, right? Just the airfoils, right? But span area becomes important in the wing analysis when we get there. Pressure and shear. So flow properties in general, right? Let's make it a little simpler. Does cause this pressure and shear on the object? Velocity, exactly, V infinity. What are the other properties of air we have there? Density, exactly. What else? Temperature, that's definitely true. What else? There is just a couple more, not that much.
Does the material of the aircraft matter? Material help?
It does matter, but let's say we have included all of it in the chord length, right? Especially the surface roughness and everything. Yeah, it is important. But the geometry is not that much of a concern in aerodynamics, so include everything in this chord length. Gas constant, but gas constant is going to remain constant, right? So the variation of it doesn't really make any sense here. What about viscosity? Do you think it's important, or probably? That's why I'm asking, yeah? That makes sense. Yeah, viscosity is very important. I mean, you guys don't really deal with viscosity that much in your fluid mechanics, or hopefully deal with it in heat transfer. That's why no one really likes viscosity that much. Doesn't get any love. And what else? I guess that's it. We can actually say these are all the things that are important. The variation of these physical quantities is going to change your resultant force. Okay. So a lot of parameters. How many? 1, 2, 3, 4, 5, 6. 6 parameters. We have to change some things here. For example, temperature. In this course, we don't really talk about aerodynamic heating, right? But one thing that is important is whether the flow is compressible or not, which can be determined by the speed of sound, the free stream speed of sound. Free stream speed of sound is a function of temperature, gamma, RT, your gas constant, the ratio of specific heat for air, 1.8, 287. That's what we usually do. So that's how it relates to temperature. But we usually use the speed of sound because it's a more important parameter in aerodynamic flows that don't include aerodynamic heating. Okay. Let's say we are talking about a flow at which angle of attack doesn't change. So if angle of attack is constant, it doesn't vary, right? So it won't affect the resultant force, right? So the important parameters for this specific case came down to just 5 parameters, right? It's a lot of inputs, right? It's a lot of parameters. If you want to study the flow of air over an airfoil or wing or aircraft in general, you have to play with a lot of different parameters. You have to change a lot of things to be able to come up with some general solution to the flow of air over that wing or aircraft, right? So essentially, it will not be a bad idea to come up with a method that will help us reduce these variations. Or reduce the parameter that we have to play with. That's where dimensional analysis comes into play. Essentially, try to combine these parameters. Yes. It does change the angle of attack, but we are just assuming that it is essentially at cruise conditions, right? It doesn't change the elevations, right? Because if you want to include the angle of attack, it is going to be a little more complicated, right? Okay, where were we? Reducing the variations, right? But the only thing that you have to keep in mind that to essentially combine these parameters, physical quantities, we have to remain consistent. We have to make sure the dimensions are consistent, the units are remaining consistent. We are not just adding up some random numbers, right? You cannot just add numbers that have different units, right? So we get the help of dimensionless parameters. I'm pretty sure you have at least heard about the dimensionless parameters like Reynolds number or the Mach number or I don't know, Prandtl number. You have seen all of these in your heat transfer, fluid mechanics, right? Right. So this is the goal. We are essentially going to reduce these 5 parameters into 2 or 3, a smaller number of dimensionless parameters, which is going to make our job easier. Let's say instead of these 5, R was only a function of 2 parameters. Then your experiments would have been much, much easier. You had to only change 2 parameters instead of 5, right? You were going to reduce complexity. So the method we are going to do then is called the Buckingham-Pi theorem. Who in this class knows what Buckingham-Pi theorem is? I'm just taking your word. 100% knowledge. You don't have to answer any questions, but who has 100% knowledge? Can solve questions? Okay, no one. Heard about this theorem? Heard about it in your fluid mechanics, huh?
I have no idea what I read. I think I saw it on Reddit or something.
Reddit?
Yeah, no idea.
Okay, okay. That's all right. Very good. Yeah, it is. You were supposed to be taught in fluid mechanics. You were supposed to be taught this in fluid mechanics, in the last chapter of fluid mechanics, actually. You did dimensional analysis in fluid mechanics, though. You don't remember? Okay, that's all right. Okay, that's all right. But you understand the concept, right? The concept of dimensional analysis and the importance of it, right? Hopefully, you understand it by now. Okay, so let's get to the Buckingham-Pi theorem. Again, the goal is to reduce the number of variations in your model in the function, right? And we're going to employ this method. The Buckingham-Pi theorem is essentially a tool that will help you find the dimensionless parameters that are important in your specific problem, right? In this problem, we want to calculate the force. That is a function of chord length, velocity, density, speed of sound, and the viscosity, right? So this tool is going to help you find those dimensionless parameters that is going to be important in this analysis, right? Okay, so what should we do here? The first step has to be to determine the number of dimensionless parameters you are going to need to be able to replace these quantities, physical quantities, right, with those dimensional parameters. How can we find those? It's pretty simple. The first thing is you have to find the primary units in your system, or primary dimensions, let's call it dimensions, in your system. What are primary dimensions? In general, kilograms time, like mass time length, right? In our system, mass time is MLT, or if you are dealing with temperature, mass length time. If you are dealing with temperature, Kelvin as well. These are the 4 in mechanical engineering or aerospace engineering that we deal with, but there are actually 7 primary dimensions. We don't really care about the other 3, right? In this course and in this specific problem, we don't really care about the changes in temperature that much because we don't have any heating. The only temperature contribution comes into play comes into play when you want to calculate the speed of sound. So the primary dimension. How many primary dimensions do we have here? Just 3. Okay. The second thing you want to find is the number of physical quantities you have. Quantities, right? The number of physical in your system. the total number of physical quantities. How many do we have here? No, we have 6, right? So the function itself is also a physical quantity that plays a role. So make sure not to make that confusion. And then just subtract the two numbers. The resulting number will be the number of dimensionless parameters you are going to need to be able to quantify this problem, right? Finding the force as a function of all of these things, right? But how should we find these dimensionless parameters? That's the next step. It is the more important step, actually. The first thing you want to do is to get all of these physical quantities to one side. All right, so essentially, I'm going to include this R into this function. I get a new function of R, C, Z infinity, rho infinity, and alpha mu infinity equals to 0. Then you have to choose 3 of these parameters. It is an arbitrary selection, but I want to say it's not arbitrary. It's an intuitive selection. You want to choose more complex parameters, more complex quantities here. More complex quantities, or force is a complex quantity, like compared to the other ones, right? That includes more of the primary dimensions. Speed of sound is a more complex quantity, as well as the viscosity compared to the other 3 that are more basic, right? Meters per second, kilograms per cubic meters, and meters, right? These are, you take these 3 and you assume all of these 3 are going to be present, or each of these 3 is going to be present in only one dimensionless parameter. Does that make sense? Does everyone follow? No. One of these 3. In this case, you are choosing R, alpha, and mu. These are literally very arbitrary selections. If you choose any of those, you should come to the same conclusions. But if you don't choose the more complex parameters, your final solutions are going to be harder to get to. Does that make sense? Okay. So we're going to choose R and alpha and mu. That has to be present in only one of the dimensionless parameters. I'm going to call the dimensionless parameters we have pi 1, pi 2, and pi 3. So your pi 1 is definitely a function of your C, but we don't know the power. It can be C squared, C cubed, C whatever. So C to the power A. Okay. C infinity, again, we don't know the power for that. C infinity to the power P. And actually, these are the side. And rho infinity to the power C. And R. R has to have a power 1. That's part of the methodology. Okay, or all of these, like the arbitrary quantities that you choose. Then let's call this F1. F2 has to be a function of C to the power, let's call it A2. It has to be it can be a different power. B infinity to the power B2, rho infinity to the power C2, and this time alpha infinity. And we have the same for F3, C to the power A3, infinity to the power B3, and rho infinity to the power C3, and then alpha infinity. No, not this time. Mu infinity. Okay, is this clear now? This pi 3, for example, is a function of c, v infinity, rho infinity, and mu. We don't know the powers of c, v infinity, and rho. Okay, let's continue. Then, after this is actually going to be very straightforward. Then our job here is to find these powers, right? Let me start from the pi 3. F3 of c to the power a3. What is that? V infinity to the power b3. Rho infinity to the power c3. And mu infinity. Okay, so what is the dimension of pi? Nothing, right? We know that dimension is nothing. It is supposed to be dimensionless. So in dimensional analysis, it will have a dimension of 1, right? What about the dimension of f? Dimension of f will be the dimension of c to the power a3, right? Multiplied by v infinity to the power b3, multiplied by the dimension of rho infinity to the power c3, multiplied by the dimension of mu infinity. Okay, do we know the dimension of c? Meters. So is it clear up until this point? Okay, that's good. So we're gonna have m to the power m a3 plus, what is the dimension of velocity? Meters per second. So m to the power b3 again, divided by s to the power b3, right? This is not plus. Kilograms per cubic meters. So kilogram to the power c3. This is just a mathematical whatever. What is that? The dimension for viscosity? Let's actually do MLT instead of mass because we want to be able to do this in every analysis. So mass, C is L, length. Then we have L over time. Sorry about that. Then we have mass over length cubed, right? What is the dimension of viscosity? Does anyone know off the top of their head? That's all right. I don't usually know that as well. Is mass or is M mass divided by length divided by time? Okay. So, and all of this has to be equal by or 1. To be equal to 1. Let's try to simplify this. Like get all the L's together, get all the M's together, and get all the T's together. So we're going to have L, we have A3, then we have B3, we have 3C1, 3C3, sorry, and then negative 1. So L to the power A3 plus B3 minus 3C3 minus 1. Does this make sense? I just combined all of the powers. then multiplied by, let's do T next, negative B3, and then only negative 1. Then let's do M. M is going to be C3 plus 1. Is this clear? Just combine all of the powers. So in order for this equation on the right hand side of the equation, in order for it to give you 1, which is the thing we have on the left side, all of these powers has to be 0. That's it. So we essentially have 3 unknowns and 3 equations. We can find the unknowns. What are the 3 unknowns and 3 equations? The first one is A3 plus B3 minus C3 minus 1 is equals to 0. The second one is negative 1. That's correct, right? Negative B3, negative 1, yeah, is equals to 0. And then we have C3 plus 1 equals to 0. From this, we can conclude that C3 is negative 1. B3 is also negative 1, right? Plug that in. 1, 1, negative 1, negative 1 here. We are going to have positive 3, negative 1, and negative 1 here. So we're going to have positive 1 on this side, and we're going to get A3 as negative 1, 2. Is this clear? Yes? Okay. So for pi 1 was supposed to be a function of C, V infinity to the power B, and rho infinity. So your pi 1 is going to be equal to mu infinity over rho V infinity C. What does this remind you of? Reynolds number. What the inverse of Reynolds number? 1 over Reynolds. So one of the parameters we have here, one of the dimensionless parameters that is going to help us in this analysis is going to be Reynolds number. If you do this analysis for the rest of them, pi 2 and pi 1, you are going to actually find the force coefficient, CR, which we remember from the previous lecture, is R over Q infinity C, right? As well as the Mach number. Are we clear on this? Yes. Yeah, sorry, that's right. I'm sorry about that. That is pi 3. As well as the Mach number, which is V infinity divided by alpha infinity. So instead of having these 6 variables, we are going to have only 3. G of C of R, and the Reynolds number, and the Mach number is equals to 0. And the goal here was to find force. So we can replace this function. Let's call it the function this time. Let's call it G1. Your CR, we are dealing with the force coefficient from now on, this analysis at least, is going to be a function of Reynolds number and the speed of sound. So essentially, you should be able to characterize any type of flow over an airfoil with a constant angle of attack with only changing these 2 parameters. If you are doing atmospheric flight at sea level. You only have to change the essentially speed, because the speed of sound is going to remain roughly the same, or Reynolds number, to get all of the results you need from this analysis. Is this all clear? Hopefully. But, so this is the Buckingham Pi theorem that is going to help you do the dimensional analysis and reduce the number of variables in your system, right? Reduce the complexity of the system when it comes to the analysis, right? This actually has another consequence, this type of analysis. And this brings up that the consequence is essentially the idea of flow similarity. Are we familiar with flow similarity? Not at all. Okay. Is there anyone who has some resemblance of familiarity with this concept, or any ideas? Yeah, so the online student we have here actually mentioned viscosity, but I didn't see it. So sorry about it. Flow similarity. Let's see. We have an answer here. Okay, Ryland here over the internet is essentially moving in the right direction. Two flows are similar if the objects that are flowing, are geometrically similar, right? So they are essentially the same airfoil, okay, or they are the same. They are both spheres, right? Not the same sphere, but they are both spheres, and the distribution of dimensionless parameters or dimensional parameters in general in that specific system are the same. So what does this mean? It means that if you do that dimensional analysis, come up with the dimensionless parameters that are important in your analysis, you can actually run tests in a wind tunnel for a scaled down version of your plane, airfoil, whatever, and apply the results to the real flow condition, right? That's the main idea of the flow similarity. It makes the Buckingham Pi theorem even more important. Any questions so far? No. Yes.
So the main outcome of the Buckingham Pi theorem is that the force coefficient is just a function of the Reynolds number and the Mach number?
For this specific case, yeah.
Okay.
But you can apply this theorem to any type of problem, right? Essentially.
Okay.
As long as you follow the procedure. Okay? You have a question? No. So if there's no question, then let's get to the example problem we wanted to solve. We are going to solve some flow similarity problems or examples in the next lecture, which are already included in the slides. But the example we are going to solve, this is a book example, but I want you to start working on this. This is an interesting example. It may look hard to deal with, but it is not that hard, as long as you understand the first steps. Okay, this is example 1.1 for the first example of the book. We have a supersonic flow over a 5-degree half-angle wedge. So we have a wedge. With a 5-degree half angle. Okay. And we have supersonic flow over it. The Mach number, the free stream Mach number ahead of the wedge is 2.0. And the free stream pressure and density are P infinity 1.01 10 to the power 5 newtons per meters. Or what is this pressure? 1.01 10 to the power 5 newtons per meters squared, or pascals. Now, what is the significance of this pressure? The atmospheric pressure, 1 atm, right? And the density of the free stream is 1.323 kilograms per meters cubed. The pressure on the upper and lower surfaces of the wedge are constant with distance s and equal to each other. So we have a uniform pressure distribution on the upper and lower. Okay? And this P of upper and lower are equal to each other, the value for which is 1.3 10 to the power 5 newtons per meters squared. We have also the pressure exerted on the base, of course, but this is equals to P infinity. And we have the shear distribution. The shear distribution is going to be the function of S. Is going to be changing with S, which is going to be 431 S to the power negative 0.2. The chord length, which is this length, is 2 meters. And we want to calculate the drag coefficient on the wedge. And you have to keep in mind that the angle of attack here is 0. Okay. The first thing you need to know before approaching this problem is that we will definitely have some shock formation here, right? But we don't really care about the shock formation because we have the information past the shock. And we don't know how to do any shock analysis. So, okay, what should we do here? And I have the equations over there, right? We want to calculate the drag coefficient. We can actually, let's do the D prime first. The drag force first. Let's do this first, and then we'll move on to the drag coefficient. We have the equations for force coefficient over there, but we have the equations for normal and actual force coefficients. And if you don't see the whiteboard over there, I'm pretty sure you can find those in your notes. We don't actually need those. So. But think about it. The angle of attack is 0. What is it going to mean for the relationship between lift and drag and the actual and normal force? Actual is going to be equal to drag and normal is going to be equal to lift. Because the angle of attack is, so the two forces are essentially on each other, are the same as each other. Okay, so we essentially can use the equation we have for the actual force, A prime, to calculate the drag force. What is the equation we have for the actual force? And this is actually, this problem is a quiz, so make sure to submit your work at the end of it to get attendance grade. Okay? Yes. Please. Pardon me? You have to submit your answer to this problem. Do you have a pen and paper you can use for it? Okay.
By the end of this class also. Like by the end of this class.
Yes, by the end of this class. That's correct. That was the deal for quizzes, right?
Yeah.
Yeah, okay. Just wanted to make sure we have talked about this before. Okay, what is the equation we have for the axial force? Let's hear it. Let's actually do this. We have 10 minutes. Whoever can calculate and you shouldn't use your books, of course, so please don't use the books unless I'm going to trust you, so you can use the book if you want to look up the equations, but don't look at the answers to the problem. Whoever can give me a correct answer or an answer for that matter, by end of this lecture, will get a bonus point. Half a point of your total gain. Pardon me? No, for the final drag, essentially.
You want us to copy down the problem so that it's way smaller?
No. Just your name and the solution. Right. We have the theta, right? Because this line doesn't have any curvature, right? So theta is going to remain constant. And if you need a reminder, theta was the angle, pressure, or the normal pressure made with the axial force. And the shear made with the normal pressure made with the normal force, or N prime, and the shear made with the axial, which is going to remain 5 degrees for all of these calculations, because we are only dealing with a line, right? Okay, so we have the theta. But how can we find ds? ds is going to be a small element on this line. So to find ds, you have to understand the equation of this line, right? Or to make it easier, you have to find a relationship between ds and dx here in this direction. Yes, actually, that may make it a little harder. No, you take the integral with respect to ds and then find the value of s at different locations, like from S1 to S2, S3, S4. I want to make sure we all get this. So whoever submits the correct answer will still get a bonus point, but I'm going to try to explain this a little better. Okay, we want to take this integral over ds, right? And this is the integral over essentially 3 lines, right? Since we are dealing with an upper surface and a lower surface, let's make it 4 lines. First line, second line, third line, fourth line, right? The initial point of the lines, let's call them S1, S2, S3, S4. So the first integral can be divided into 2 integrals. The integral of this whole thing from S1 to S2, okay, on that line. And then again, the integral of this whole thing from S2 to S3. Then for the lower surface, we're going to get the integral from S3 to S4 and from S4 to S1 again. Does this make sense? No. We have 1 no. This is a no. Do you have any maybes? 1 maybe. And a lot of people are not yes, no, or maybe. Okay, that's you have to make sure you understand this type of integration, because this is something we will come back to, especially in your exam.
Do we know the base, if you will, of the triangle? Do we know that distance or no?
Which distance?
Like the base of the triangle, I guess, like on the right side.
This?
No, that's 2, right?
That's 2, yeah.
The distance on the right distance, like S2 to S4. We know S2 to S4.
Okay, that's a good question. I'm going to come back to this. Let me answer the Ryland's question. I have labeled these S1, S2, S3, and S4. You can label them as whatever. What was your name?
I'm John.
John. John is asking whether we know this distance or not. Right, that's your main question, right? Okay, so I'm going to pose a question to class. We have this is 2 meters, right? And we have this angle. Do we know this length? Yeah? That's tangent relationship. Can you repeat your question? Here, the variable, we have PU, pressure on the upper surface, tau of U, the shear on the upper surface, then S, which is going to be your surface, right? The line here. We have a PL, pressure on the lower surface, tau of L, the shear on the lower surface, and the sine and cosines. But since the geometry is just linear here, sine and cosines for S1 to S2 is theta is going to be 5 degrees. For this one, theta is going to be 90 degrees, right? Because it is perpendicular to your coordinate system. Again, whenever you want to determine theta, okay, it's good that you start solving this. Let's say this is your chord length. The idea was this is N prime, right? And this is A prime, right? In this case, it is L prime, D prime. Does it make sense? Theta and pressure, and this is specifically one pressure, is normal to the surface, not the chord, right? To the surface. Tau is tangential to the surface. Theta is going to be the angle this surface makes with your chord. Okay? So what is the angle this surface makes with the chord? 90 degrees. What is the angle this surface makes with the chord? 5 degrees throughout. Okay? Does this make sense or not? Yes. 1 yes, 2 yes, 3 yes. Does it make sense? Okay, more yeses. That's position, yeah. Okay. That's essentially this. So this position here is identified by S. It is not X, it is not Y, it is identified by S, right? The position on the surface is always identified by S. Okay?
So lower, upper, this is the lower quadrant, this is the upper quadrant.
That's right.
And then, so we just have to find the total distance traveled there. And it's equal to the total distance traveled there.
What's that? The total distance traveled here.
So we have PU, we have PL. We get TU and TL from this equation, from the
That's right.
equation. And that would be the total, because PU is equal
So let's
to
say
TL,
S.
PU should be equal to TL, right?
But yeah, essentially. It's the
So
same.
that should be the distance traveled from here to here to here.
Exactly. So your tau is going to change with distance, right? So tau here is going to be different from tau here. Does it make sense?
At the tau we're using
inside this equation is the total, right?
No, you're taking the integral, right? That's the point of taking the integral. Inside the equation, you don't have the average. Let me see. S, okay? So what is the integral of a constant value is that constant value multiplied by S, right? What is this integral? The integral of 431 S to the power negative 2.
We just change this into ds, right?
For
amount
it,
will be here, right?
no, you cannot just. Are you talking about the difference between DSU and DS? Is it? This is SU, right?
DSU is not equal to DS.
DSU is just referring to DS on the upper surface, whatever that is, right? You can,
Already in terms of s.
but you have to keep in mind that this is two different integrals, right? The first one is DS on this surface, for the upper surface, and then we have another integral on this surface. Okay, so we will get the integral of leading edge to the trailing edge, whatever that is. For the case of S, we're going to get the integral of S1 to S2, okay? This constant plus tau of u ds, right? Plus the integral from S2 to S3. Again, coming back to him, whatever that P is, whatever that tau is, ds. Okay? So these U's and L's are just representative of location, right? This is just representative. These are DS's, but the SU refers to the S on the opposite. Yes.
So we still have the before, and it was S1, S2, S2, S3, S2, S4, S4, S1.
That's correct. That's correct. That's correct.
All with the same parameters.
You can put it over there. Put it over there. Pardon me? Sorry.
All with the same parameters. You're just changing the angle, right?
No, like P is going to change, right, on this surface. Theta is changing, P is also changing, right? Because we said on the base, P is going to be P equals to P infinity. Not this. This is not P. Drawing. Yeah, it's not this PU and PL, right? P is P infinity.
Okay. But
That was.
But on the upper and lower surfaces, it's 1.3.
That's correct. That's correct.
I see.
Yeah. This is in the book. Yeah.
It's not using it.
So from S3 to S4, it's just straight up the infinity.
P infinity is not PU or PL. P infinity is the free stream pressure or one atmosphere, right? Just the number is different. Right? That was in the statement of the problem. Okay? So, pardon me?
The signs, the negative, positive, but it's always the negative. What are those?
So let me ask you this: what is going to happen to this integral on this surface? What is theta on that surface again? 90 degrees. So what is cosine of 90?
0.
0. What is sine of 90?
1.
Okay, so the shear stress is not going to contribute to drag on that surface. So you're going to get the integral of PU ds, integral of PL ds. So essentially you're going to get PLS, which is PL multiplied by this length, negative sign, plus PLS, PL multiplied by, that's on the lower surface, PL multiplied by this sign. Does it make sense?
I think so. I should have worked it out. Cancel out a little bit in the back of the model.
That's something we didn't cancel lift and drag. It will cancel out lift, that's correct.
Yes. So,
But it doesn't cancel out drag though.
so how do we get drag on
That's the idea. When you have, so lift and drag are perpendicular and tangential to the flow direction, right? actual and normal force are perpendicular and tangential to the chord, right? What will happen to those forces when the chord and flow direction are essentially the same direction? Pardon me? So you understood the statement, right? What is the lift and drag compared to the flow direction? What is the actual normal force? Okay. Then in this problem, since the angle of attack is 0, the flow direction and the chord direction are the same direction, right? Which means that lift is the same as your normal force, because they're going to lay on top of each other, and drag is going to be your actual force. So as soon as you calculate your actual force, you have your drag.
I guess that's true for the rest of the experience.